So, we're going to do a practical. And we are going to test the accuracy of different bits of laboratory equipment. Because all of these pieces of laboratory equipment have measuring things on the side. So this one will do 50, 100, 150, 200 millilitres. This one will go up to 100 millilitres. Come on, guys. Chop, chop. Measuring cylinder and volumetric flask. Okay, so we're going to measure the accuracy of these pieces of equipment. Now then, taking into account the relationship that we established before, 1 centimetre cubed equals 1 millilitre equals 1 gram, how might we be able to measure the accuracy of... How might we be able to measure the accuracy of a measuring cylinder, taking into account what we learned? So, if I put in 100 millilitres of solution into this, taking into account the fact that I'm not actually weighing the jug itself, what weight would I expect 100 millilitres of water to? 100 grams. Because 1 millilitre is equal to 1 gram. So if I fill this up to the 100 millilitre line, taking into account that I'm at eye level, taking into account the meniscus, and you do need to fill these things accurately, so do fill these things as accurately as you can, then I should be able to weigh just the water and find that it equals 100 grams, if this is accurate. If it's not accurate, it won't weigh 100 grams. Okay, so this experiment is all about measuring the accuracy of these pieces of kit. Okay, so just thinking back right to the start of the lesson, what's the first thing we do before we plan the experiment or anything like that? Where do we start? So we make a guess, which we would call a hypothesis. So to start off with, before we even do the experiment, we need to make a prediction that we can then put to the test. So let's just take a quick note of that. I do this lovely breathing thing and then forget what. Okay, so some notes for you guys. Okay, so once you've written that first paragraph, what I'd like you to do is just looking at the 4 pieces of equipment: volumetric flask, measuring jug, measuring cylinder, and conical flask. I would like you to make a prediction. And you can do one of 2 predictions. You can say, I think that the conical flask is going to be the most accurate. So that could be a prediction. So I think the conical flask will be the most accurate out of the 4.
Do you have to say why?
Don't have to say why for a hypothesis. You're just coming up with an idea which will then put to the test. So you don't need to justify it, you can just make a prediction. Or you could say, I think the measuring cylinder is going to be the least accurate. So you can make one of 2 predictions. Either I think A is going to be the most accurate, or I think B is going to be the least accurate. Both of those are a valid hypothesis for this. So I want you guys to come up with your own... the only piece of equipment that we've got to add to that is one of these things. These are called top pan scales. As just an aside, the amount of students that I've seen pop in a thing on there and then saying it doesn't work, you do actually have to open the lid to get it to weigh something. Okay, so just bear that in mind at the end of the experiment.
It doesn't look like it.
Okay, so they're the pieces of equipment, and they don't really interact so much. So the apparatus diagram for this is fairly straightforward. But please do label it. So this will be measuring jug. Okay, so we've done our hypothesis, we've done an apparatus diagram, so we know what we're going to use and we know roughly how we're going to set the whole thing whole thing up. Does anyone know what the last thing we need to do is? Actually, there are two things that we need to do before we start the experiment. One of the two things? Go on, Michelle.
Method.
Yeah, we need to do a method. And Veronica, what's the other thing that we need to do?
Specs.
Yeah, kind of. We need to do the risk assessment, which would include safety specs. Yeah, so a method and a risk assessment. Just in terms of diagrams, it is a good idea to do diagrams in pencil when they get a bit more complicated, because you can rub pencil out and you can make changes to your diagram. So it's just, again, it's a good habit to get into. Okay, so last page of note copying for you guys, and then we'll get into the experiment proper. Okay, just to go over what the method steps are telling you, you'll be working in teams of 5. But just to reiterate, get the piece of equipment empty without any water in it, pop it on the top pan scales, and let the top pan scales read the weight of the piece of equipment on its own. So they're roughly 95 grams odd. So once it's stopped moving around, they settle on a weight, press the 0 button, and it will take the weight of the scale back down to 0. And then you can take that off, put 100 millilitres of water in it and put it back on the top. And then you are only measuring the weight of the water, because the scales have already taken into account the weight of the actual vehicle itself.
Do the scales all the time out?
No, I don't think so. Or if they do, it's a long thing, so you shouldn't have to worry about that. Okay, so put it onto the piece of equipment, onto the scales empty. Let the scales register the weight and hit 0, and it will bring it back down to 0 again. You can then take the piece of equipment off, put 100 millilitres of water into it, and pop it back on top of the scales. And the weight that you read off will be just the liquid, and not the piece of equipment and the liquid. Okay. So I'm going to hand out these risk assessment forms. Now that you know how the experiment is structured, just have a quick think about the risks. Have a think about, don't write them on the sheet just yet. We'll just go through them before you write the before you fill this sheet in, so that you've had a rough consideration of what's what. But they didn't need to be. That's fine. Don't worry about filling in everyone. Title of the activity is obviously the Great Accuracy Experiment. Or just the accuracy experiment, if you don't want. Superlatives.
Yeah,
Okay, and then there's this outline of the procedure. You don't need to go into great detail for this, but you do need to show that you've just appreciated which chemicals are being mixed with which, if we're mixing chemicals, or what the outline, an overview of the experiment is. In this case, you can say measuring the accuracy of the equipment using water and scales, and top pan scales. That just picks out the key bits. We've got laboratory equipment mentioned, we've got the water mentioned, and we've got the scales mentioned. Okay, the 4 columns we don't need to worry about in this experiment because we haven't got any chemicals that we're mixing. So we don't actually, these ones tend to be are we actually synthesising anything by mixing chemicals together? And if so, what are they? The thing that we are interested in are the 2 columns underneath, non-chemical hazards and precautions for non-chemical hazards. So what are some of the hazards associated with this experiment? So we've got some glassware. So there's a potential hazard in the glassware. So in the right-hand column, non-chemical hazards, you could put glass.
What about the water if you spill it on the floor? Is that just being a little bit?
Excellent. No, that's good, Sasha. Hold that thought. We'll come back to that. So glass, and the precautions can be as simple as just being careful when you're working with glassware. And if you smash the glass, then glass does get smashed, so don't worry about breaking laboratory equipment. It does happen from time to time. Just give me a shout. I'll sweep it up and I'll put it in the glass tube that we've got. So just let me know if you smash glass. The precautions can just be taking care when using glass. So go on, Sasha, tell us about the other hazard that we've got to watch out for.
In case of PVs in water, there have been plugs around or just going on force and slip or you could.
Yes. Yeah. That's the other, or one of the other key hazards is the water. We're using water and electricity, and those two things don't mix. So we need to be, again, we've got to be careful when using the water. Don't fill the pieces of equipment up whilst they're on the scales. Take them off the scales, fill them up, and then put them back on the scales, for example. And also, if you spill it, then you clean it up quickly. So glass scales and electricity is the third non-chemical hazard, really. And just if anything electrical gets wet, turn it off at the plug socket. Don't touch it, just turn it off at the plug socket. And they're the three main hazards here. Disposal of residues we don't need to worry about in most cases, unless you can pour the chemicals down the sink, the stuff that we use here. An emergency action is let the tutor know if anything goes wrong. A couple of points for good laboratory practice. When you're doing an experiment, do it standing up. If anything goes wrong with the experiment, you spill it or anything like that, you need to be able to get away from it. If you're standing up, you can just step back and you're out of the way. If you're sitting down, you can't do that. So when you're doing an experiment, do it standing up. If you can make sure your bags and such like are just tucked out of the way. Actually, and that includes stools, because there will be a lot of stools dotted around, and we have got a lot of people in this class. So you need to make sure, particularly the stools at the back, they're tucked under the desks and the bags are under the desks too. If there are bags in the runway and they're getting in the way, then they can go up against the wall. But we just need to make sure that we've thought about the fact that there are bags around. And also the surfaces, if you can just make sure that everything's piled up together, so you haven't got pens and paper and all that sort of stuff in there. Hey, I meant to tell you one other thing there. Oh yeah, results table. There is a results table which I've got for this, but when you're taking results in an experiment, it's not important for you to write them down neatly. Just have a scrap of paper, and the results table will look a little bit like this. Measured volume, which will be 100 millilitres for them all, and then what the weight of the water is in the zone. That's basically what the results table will look at. But just have a scrap piece of paper to record results, which you're putting in this, the table still. Just what could go in this accuracy section? What's the possibility to get a measure of the accuracy of each of those pieces of equipment? What could we put in there? Yeah, we could take it away from 100. But what if the conical flask had only measured 75 millilitres in the conical flask and it came to 74 point, Say again, Abby? Not necessarily minus. There's a bit of maths that we could use. It's not rounding. No.
1, 2, 3, 4.
You said percentages. Yes, we could work out a percentage. If we had measured different volumes here, we could actually work out a percentage and get a percentage accuracy in this column. Now in this case it's easy because actually we used 100 millilitres, so actually that's 98.61% of 100 millilitres, purely because of the numbers that we've used. But if we'd measured, say our volumetric flask had only measured 75 millilitres, then we could work out. Okay, because the last thing that we need to do is draw a conclusion. Now you have to draw a conclusion from your results. You can't draw a conclusion from my results, which are on the board, because your conclusion has to relate to your results. So if you're
bit copied out there?
Yeah, the bit at the top, please, because this is a framework of how you would do an experimental writer. That's what we've done today. But your conclusion has to relate to your results. So if your results tell you the conical flask is the most accurate, and your hypothesis was that the conical flask is the most accurate, then your results prove your hypothesis. So your conclusion has to relate to your results. Let's have a look and see what results you did get. So hands up if you got that the measuring beaker was the most accurate. Any measuring beakers? Nope. Hands up if you got the conical flask was the most accurate. Okay, so one's group got the conical flask as the most accurate. Hands up if you got the measuring cylinder as the most accurate. Any measuring cylinders? And hands up if you got the volumetric flask as being the most accurate. Excellent. Okie dokie, that's great. And actually that's quite a good way of getting a more accurate result, is you can actually start to combine results. Veronica, you mentioned repeating the experiment. And you can repeat an experiment and that will increase your accuracy, because you can start taking averages, which is a way of increasing accuracy. Or you can get lots of groups to do the experiment and take an average of all of the results, which again is another way of increasing accuracy. And actually, the volumetric flask is the most accurate. Hands up if your hypothesis was correct, if you said that you thought that this was going to be the most accurate. Right, a few of those. This one is the most accurate, and actually now that you guys have used it, you've had a chance to have a look at it. I mean, it only does one job, and that's measure out a fixed volume of fluid, so you would want it to be the most accurate because it doesn't do anything else. It does say on some of them, although actually yeah, on most of them, at 20 degrees C, so it does specify a temperature range under which it should be used. And it also has the line which goes all the way around, so actually getting to eye level is much easier because you can see both sides. And when you can see two lines, you're not at eye level, and when you can see one line, you are at eye level. So again, it's trying to help to improve accuracy. So yeah, you would want this to be the most accurate. What we've learned overall, and just the measuring cylinder and the measuring jug both say approximate values. What we've learned overall is if I ask you guys to measure a volume of liquid accurately, I don't want to see you reaching for a measuring jug or a conical flask. I'd like to see you reaching for either a measuring cylinder or better still, volume. Okay? Least accurate measuring jug or the conical flask. Conical flask traditionally seems to be a little bit more accurate, but neither of them are particularly.